I'm going to touch on adaptive management for low-tech process-based restoration, or really any restoration project you might be involved in. But since we covered much of this in the conservation planning process presentation in Module 4, which is really based on adaptive management, we're going to emphasize some of the key components of adaptive management that were not covered in that previous talk, mainly the learning component. We will also further emphasize the importance of promoting through maintenance until we have a self-sustaining system. As we stated earlier in the course, much of what we are doing has been done in some form. While we might emphasize different aspects of this restoration, there are examples over the past 150 years we can point to that use similar approaches. And so while not new, this type of restoration perhaps was forgotten, was replaced by more highly engineered approaches. So it might be more accurate to state that low-tech process-based restoration has been rediscovered. So in many ways, this type of restoration may seem somewhat novel to some. And recall, we also stated that restoration in general is lacking support of the claimed benefits these actions provide. Well, I would say there's as much or even more evidence backing up the effectiveness of low-tech process-based restoration. Like traditional restoration, there's much to learn about these approaches. And examples of low-tech process-based restoration projects addressing different goals keeps growing. Here are some examples: increasing vegetation production within riverscapes, habitat improvement for a diversity of animals, and several ecosystem services such as increased resistance and resilience to disturbances, storing water to increase flows during the summer, increasing forage for cattle, storing sediments, and mitigating non-point source pollution. We want to encourage you all to keep adding to this list, and if possible, document if and why low-tech process-based restoration works. Perhaps more importantly, you want to prove to yourself and to your stakeholders that your restoration approach actually worked. Adaptive management is most appropriate for novel restoration and management approaches where concerns and alternative responses can be vetted and tested, and where we want to increase our understanding to inform future application of these approaches for your collaborators. Here's a classic adaptive management loop of plan, do, evaluate, and learn, which can inform adjustments needed to reach restoration goals or improve learning. The way I like to think about adaptive management is really applying the scientific method to management. So here's the outline of my talk, which is basically going through these different components of the adaptive management loop. So let's talk a little bit about planning. And remember, Joe's talk in Module 4 on the conservation planning process is basically adaptive management. And while there are internal checks and adjustment to these phases, we encourage people to revisit earlier phases and make potential anticipated adjustments if needed. So I'm going to further add some discussion to the planning process. What likely prevents the adoption of adaptive management to be more common is the emphasis placed on the planning phases and the classical approaches originally presented by Walters and others. In these examples, a huge amount of effort is put forth to understanding the system, identifying concerns, and reducing uncertainties through complex modeling approaches and developing testable hypotheses. But the management problems were huge, and the potential to do harm were significant in those examples, such as a completely different approach to managing a multi-billion-dollar ocean fishery. So you better minimize the potential to do harm as best you can before implementing an experimental approach. But we are often working in areas where a lot of effort has likely been put forth in identifying the problems and goals, such as sub-basin plans to recover salmon steelhead in almost every basin in the West. This is a huge starting point for us to springboard off of. And the low-tech process-based restoration is often implemented in wadable streams where the risk of causing harm to infrastructure and even populations of targeted species is quite low, although this is obviously dependent on scale. That said, there are still things you can do to increase your ability to learn and achieve success. We encourage people to come up with a model of the mechanisms how you think your restoration will address your goals and objectives. This doesn't have to be a complex model, but could just be conceptual. I think you'll find that working through this thought process will help you articulate your hypotheses, or another way to say your predictions, that you'll be addressing with your restoration and your monitoring. This is the conceptual model I showed in Module 2 about the Bridge Creek Intensely Monitored Watershed Study. A similar approach can be used to describe what geomorphic responses you expect to kick off with each structure type. We refer to these as design hypotheses. This is far more specific than the conceptual model. This can help you identify what you know, suspect, versus what you don't know, and may seek the help of others that have more experience. The conceptual models and associated hypothesis and the design hypotheses should be shared with multiple stakeholders. What adaptive management encourages is the development of alternative hypotheses. So work with your stakeholders to identify these alternative hypotheses and potentially flag concerns. Your hypotheses and alternative hypotheses will lead to the development of monitoring and potentially triggers that may lead to modifications in your approach. For example, on a project I was working on, there was concern that BDAs and beaver dams would tip the scales in favor of exotic brook trout, further leading to declines in the native cutthroat trout. So if your hypothesis is that BDAs can lead to an increase in cutthroat trout, an alternative hypothesis would be that this would lead to a decline in cutthroat trout due to an increase in brook trout. So the monitoring would have to include fish monitoring, and a trigger could be that a decline in the cutthroat and an increase in brook trout requires the removal of BDAs, which can be a very quick process. Let's talk a little bit about developing designs. In order to determine whether your project has promoted processes, has become self-sustaining, has tripped triggers, is achieving objectives such as benefits to targeted species or whatever you identified as worthy to learn about, to inform future efforts, you're going to have to monitor. In general, you are trying to detect change, and the best way to do that is a combination of maximizing your contrast or minimizing your measurement error. You'll need to think about what you're going to monitor. This is the response design, and will include considerations of how to reduce noise or the measurement error. And also where, when, and how often, which is often the survey design, to maximize contrast. In previous talks, we've talked about some of the metrics that might help evaluate riverscape health and responses to floodplain reconnection. Also, your conceptual model, hypothesis, alternatives and concerns, and design hypothesis should guide what to measure. Pre-project information is always going to make your contrast greater to show change, but in the case where this was not done for a huge number of reasons, you might have to see if you can see change through time. This is an after-only design, and it's basically trend monitoring. Big changes may be detectable, but they may also be due to variables that have nothing to do with your restoration, such as climate. So you have to account for some of these changes using covariates. This is an example Jeremy showed in Module 2 where change in vegetation production increased after changes in grazing management and the expansion of beavers in Maggie Creek. They used a covariate precipitation to show that this was not a major driver responsible for the change, and it was more due to these grazing practices. Again, having pre-restoration monitoring is preferred. If you have this, you can compare this to changes after restoration. This is referred to as a before-after design. For instance, on Bridge Creek, we had beaver dam counts beforehand. We had a long time series that the Bureau of Land Management conducted prior to us adding beaver dam analogs. So we were able to compare pre-restoration averages to the post-restoration averages to show an increase in beaver dams. This is again from the Bridge Creek Intensely Monitored Watershed study that I talked about in Module 2. If you have pre and post information and you have the same information on a control, you're now creating contrast and accounting for potentially several covariates. This is referred to as a before-after control impact, or BACI design. By subtracting your control values from your treatment values, you are filtering out noise common to both. So note how both the treatment and controls bounce up and down. They're often doing it together. And this can be due to seasonal conditions or ocean conditions that were common to both your treatment and controls. And so when you compare the average difference pre to post, this is a much more powerful design. And we can get into even more complicated designs, such as the staircase design that Steve talked about in the Asotin Intensely Monitored Watershed study, where we also had treatment and control, but treatments are implemented in a staggered fashion to help replicate initial conditions. And this is potentially more powerful than BACI design. But it also may be more feasible, rather than having to treat 4 kilometers of stream for all 3 streams in a single year. We only do 1 stream per year. So there's a lot of resources on this stuff, or you can hire people like ourselves to help with these designs. So once you have your monitoring and restoration designs, the next phase is to implement the restoration. If you don't know what to expect, and you would like to know more before you commit to, say, adding 200 structures, you can start with a much reduced number that we call a pilot. We do this frequently, even though we have a fair amount of experience, just because every system has nuanced differences. Another reason we do this is sometimes it helps to make the project stakeholders more comfortable with the approach. Depending on the results, you might go back and adjust steps within the planning process before the full-blown implementation. For example, these are pictures we built in the Asotin prior to full implementation. What we learned is that structures meant to create a scour pool by creating a constriction jet had to be extended to 80 to 90% of the channel width rather than only 50% as in these photos. Also, we didn't cross the post over the wood, which allowed the wood in some cases to float up and get taken downstream. So those were modifications we did when experimenting with this somewhat new approach. Or try something you think will likely fail, but if it didn't, could save you a lot of time and money. So for example, we put in just post in 2011, and in 2012 during high flows it collected some material. You can see the eddy downstream, and by 2017 the structure had racked up a lot of material. So we put some Velcro in the system, and eventually we had wood accumulation. It worked eventually, but obviously not immediately. So it was worth testing, because if it did work as in collecting debris, this would have saved us a lot of time in the construction. So as we stated, you also have to monitor, and this may be monitoring for different geomorphic responses, habitat responses, or fish responses. Let's talk about the evaluation and adjustments. Part of learning from what works and what doesn't is sitting on your hands when the tendency is to always tinker. That's referred to as trial and error. We can actually learn a lot with trial and error, but it's far harder to identify when things are not going as planned. This is a tendency to never be wrong if you keep changing your hypothesis after you've done your manipulations. Or learn from your mistakes and document and transfer knowledge. We have developed some simple dichotomous keys to articulate when to leave it alone or when to replace or improve structures. This dichotomous key is for individual structures. This may seem like a lot of work, but once you've done it a few times, you don't have to step through this in a linear fashion. You can make the call really quickly. We have a similar process for the complex. This is a scale where you make the determination whether you are starting to promote the processes, or you still need to wait, or maybe mitigate, or move to the next phase of the restoration project. Or you might consider the restoration self-sustaining and you're done. What is important about these structure and complex evaluations that should happen annually at least is the identification of whether you need to maintain the structures to promote the changes that are necessary to move to the next phase. This process of, say, adding wood to pals or patching up BDAs can be very quick and economical and continue the trajectory towards promoting processes. Finally, the evaluation of information from monitoring will be critical to determine if your goals and objectives were met and your predictions were accurate. For example, recall that in Bridge Creek we predicted that if beaver and beaver dam analogs grade the channel and reconnect it to the floodplain, that during high floods power will be dissipated across the floodplain and prevent further downcutting or incision. And we were able to observe just that. This is a photo after a huge flood event, and the once 8-meter channel did not incise again. Instead, the water is spread out about 65 meters in some places over the floodplain. So here are some takeaways. Adaptive management can increase learning to inform future efforts, but at the same time help achieve your restoration objectives. It helps articulate your goals, your objectives, your hypothesis or predictions, and concerns. Adaptive management requires monitoring, which increases your vigilance to your project. It identifies opportunities and identifies when maintenance required and potential adjustments to achieve your goals. It also helps identify success, and this can be communicated to your audience. And finally, adaptive management sounds intimidating and can be intimidating, but it doesn't have to be complicated, especially in these systems that we're working in, where the potential to do harm has been greatly reduced.